a small introduction. So today's guest is Harsh Patil. He is graduated recently from IISER Bhopal in 2021 with BSMS, and he's done his MS thesis under Dr. Kashyap Rajiv Sarthi on Berman-Hilden theory, if I'm not pronouncing it wrong, and he has joined for PhD at University of Bristol. So maybe if you could start with in like explaining your MS thesis if you want to, and then proceed to the talk. I welcome you to the talk. Am I audible? Okay, think is not there.
Oh, hello. Sorry. Uh, Hi. I was saying that rather than talking about my MS thesis, I prepared this presentation in to sort of explain the area that I'm working on currently. If that's okay, I'll just speak
Yeah,
about that.
that's okay, completely okay.
Okay, great. Okay. Um, so currently I'm a PhD student, and I work in this area called geometric group theory. And so what we do in geometric group theory is that we study groups using group actions on certain metric spaces or um, or simplicial complexes, and so on. Uh, so and so in my today's talk, I'm going to highlight two such nice results, where where a group action has been used to uh, sort of deduce certain algebraic fact about the group. And so let us start by defining group actions. So let G be a group and X be just a set for now. And so a group action alpha is a function. So this is a function from G cross X to X, such that it satisfies these two conditions. Uh, so what this means is that every element of the group gives you a permutation of the elements of the set, and so associated to each group element, you have a permutation. Uh, Sorry, you have a map from X to X, and you can call it alpha G, which sends X to alpha G X, and this association uh, this association of G to alpha G is a group homomorphism. Is a group homomorphism. So so this fact is captured in this in the second condition that we're looking at. Um, so when we apply alpha h first, and then apply alpha g later, that's the same as applying alpha of g dot h. Okay. This definition might look abstract at the moment, but it'll become clear when we discuss some examples. So now, earlier X was just a set, and now uh, we, we can put additional structure on X. So now suppose X is a metric space, and we have a group that acts on X. Uh, Now we want that group action to satisfy that group action to respect the metric structure. So we impose the additional condition that each of these maps, x goes to alpha x, is an isometry of x, in the sense that um, distance between alpha g x and alpha g y is equal to the distance between x and y for all g belongs to g and x and y belong to x. Okay. If you are unclear about anything, and you have some doubt, you can stop me and ask questions. Okay, so let us discuss a few examples. Okay, so the let us start with a simple example. Let us consider the group z square, uh, and it acts on R2 with the Euclidean metric uh, by translations. So if mn belongs to z square and we're acting it on a point xy, then we just get x plus m, y plus n. Okay, and now let us look at something slightly more. Uh, so let O2 denote the group of matrices. They belong to GL3R, such that A transpose A is equal to identity. So some of you might have seen this before. It's called the orthogonal group, and it preserves the inner product on uh, it preserves the usual inner product on R3, and it more specifically it preserves the unit sphere. So okay, so this is O3 actually, and O3 acts on the unit sphere um, by rotations. So every element of O3 can be visualized as so there is some axis, and some axis, and it fixes this axis, it fixes these 2 points, and it rotates your sphere by some angle alpha. Okay, so O3 acts on S2, and S2 can be given it can be given a metric. It's called the round metric, and it's just so given 2 points. You just take a meridian which joins these 2 points, and the length of that meridian is the distance between x and y. And O3 also preserves this metric. It acts by isometries on S2. Okay, now the third example, you might not have come across this group. So it's called the free group on two letters, and that's something that we are going to discuss later in the talk. So I'll just write this down here, and we'll come back to this later. So The free group on two letters uh, acts via isometries on. So I suppose most of you have come across graphs. So a graph with without cycles is called a tree. And what we're looking at here is the four regular tree. So you start with a point, you draw four edges, and then you make sure that each point has valency 4. So you add three more at each point, and you do this infinitely. Okay. So and you do this a third time and again and so on. So it's a bit, the image looks like a sort of a fractal, and the free group on two letters acts on isometries uh, on this tree, on this tree. So um, yes, okay. So we'll come back to this later. So what is a free group? So let S be a set, um, and for each S belongs to S, we construct this set S inverse, which will serve as the inverse, as the set of inverses of elements in S. So S inverse is just a copy of S. So we add S in small s inverse for each S belongs to S. Okay, and now we take the set T, which is just a union of S and S minus, and let T star denote the set of all words that can be written using symbols in T. So suppose S was just A and B, and S inverse is just A minus and B minus. So T star will contain what? T star will contain, so it will contain the empty word. That's something we have to sort of throw in, and it will contain the singleton A, B, A inverse, B inverse. It will contain two letter words like A dot A, which is just A square, B square, AB, AB inverse, and so on. It will contain three letter words, four letter words, and so on. Okay. So now what we want to do is that we want to identify certain words. We don't want A and B inverse to be separate words. Okay. So what we do is that so if whenever we see B and B inverse, or B inverse A inverse, A inverse A, B inverse B, whenever we see such combination, such letters consecutively in a word, we remove them. So let's say you start out with a word which looks like A B B inverse A B square, then you just remove this. You replace this with A square B square. Okay, and this process is called free reduction. Okay, and at whenever you start with a word and do free reduction, at some point you will end up with a word which can no longer be freely reduced, and such words are called reduced words. And the free group is exactly the set of all, so the free group on S is exactly the set of all reduced words in T star. And the group operation on this is that, so let's say you have a word and another word, W prime, then you can just write them next to each other, and that will give you a new word. So let's say you have uh, a b a square b inverse, and W prime is equal to a square b inverse b inverse. Then the group operation is just write W a b a square b inverse a square b inverse b inverse. Yeah, so that's the word. And sometimes what will happen is that after writing them next to each other, you will have b and b inverse next to each other, or a and a inverse next to each other. So after concatenating, you should the next thing that you need to do is free reduction. So the group operation is here is group operation, um, concatenation plus free reduction, right? Um, okay, so let's come back to the example that we discussed above. So um, this is the let's take the two element set S is equal to AB, and let's consider the free group on this. And now so I claim that this group acts via isometries on this tree. So first of all, this tree is a metric space. So what you do is you any graph is a metric space actually, and this is just a special case of that. So any two vertices have uh, have a bunch of edge paths between them in any graph, if the graph is connected, of course. And what you do is you pick the path which has minimum length, and that the length of that path becomes the becomes the distance between those two vertices. And so now so now the free group on this two element set acts via isometries on this tree. So what it how does it act? So it just shifts this point to this point. So E shifts this point to this point, and the picture at every point looks the same. I'm sorry, this drawing of the tree is not very good, and B moves this point to this point, and the neighbors of the point move accordingly. Okay, so so yeah, so now we are going to look at a really nice result called the ping pong lemma. And so what does the ping pong lemma say? It says that, let's say you have a group G, and G is generated by a list of elements G1 up to GK. There's some finitely many elements, and they generate the group. Uh, and let's say this group acts on a set X such that um, X is a union of X1. So it's a disjoint union of X1, X2 up to Xk. And this and the second condition is that Gi maps uh, the set Xj to uh, xi, so it maps every other set other than xi itself to xi. So let's say you just had two, right? Let's say you just had two group elements a and b, then you had two sets xa and xb. So it says that any power of a should map any power of a to the power k should map xb to xa, and any power of xa should map any power of b should map uh, xa to xb. And we don't really know where we don't really care x uh, where powers of a map xa and powers of b act on xb. That's not important to us. So and so if such a condition is satisfied, we say then the conclusion is that G is isomorphic to a free group of rank n. So what this means is that there is a set of n elements, x1 up to xn, and G is isomorphic to the free group on S. Okay, so let us see how that works. Okay, so we have a we have a homomorphism from um, so here I've just taken S to be a group of n elements. Well, let's stay consistent with the notation, and let's take S to be a group of k elements, and so we have a homomorphism from f of S to G such that defined by sending xi to gi. And um, since the collection g1 up to gk generates the group capital G, uh, this phi is surjective. Okay, and now we just need to prove that need to prove that phi is injective. Okay, so how do we do that? So we have to show that every reduced word, um, so if w is a reduced word, then phi of w is not trivial. Okay, so let's say w is a word in x size, and let's say it's something like xi1 to the power n1 up to xin to the power uh, okay. So I L to the power n L. Okay, so and then VW will be just GI1 to the power N1 up to GIL to the power NL. Okay, and so so now we must show that this phi of W is non-trivial, and by conjugating phi of W suitably, we can arrange such that GI1 is equal to GIL is equal to G1. Okay, so for example, if S were just A and B, okay, and we had a word that did not, uh, you know, says that. So let's say we had a word something like A square B inverse A cube B. So here the first and the last alphabet is not the same, but we can conjugate it by say A uh, inverse at one place. Yeah. So now this will become A cube uh, B inverse A cube B A inverse. Okay, the powers might be different, but we just want the letter to be the same. So now and the fact about one fact about conjugation is that g x g inverse is not equal to identity if and only if x is not equal to identity. Okay, so conjugating uh, uh, doesn't make much difference. Okay, so now we have this word which starts and ends with g1. It's g1 some word and then g some power of g1 again. So this is some power of g1 and some of the power of g1. And so now we take x belongs to, let x belong to xi, where I is not equal to 1. Okay, so now and we apply this word on x. Okay, so now g1 to the power g1 to the power bx will belong to x1 because that's part of our hypothesis that g1 maps all other sets to x1 and so on. Okay, and now let's suppose that the next one is something say the next one is gi, then that will map x1. So the next one the next term in the word will be something gi where I is not equal to 1. So it will map g1 to the power bx to some set uh, it'll map it to us to some xi which is not equal to 1. So it will map it to xi not equal to 1, and when we reach the end we can conclude that what we have here does not belong to x1. but then g1 to the power a will again map it to x1. Okay, so we started out something which did not belong to x1, and we showed that after applying this, after acting on it by the group element, gx belongs to x1. So g cannot be equal to the identity because it acts non-trivially on a certain element. Okay, so the name of the lemma is called ping pong lemma, and it's like we are playing ping pong. It's like we are bouncing between these sets. So and it has a lot of good applications. There's a lot of fun applications, and we'll look at one such application. So let's consider these two matrices. So a b here belong to sl2z, and sl2z acts on z square by left multiplication. Okay, and let's consider these two sets xa and xb, which is that the first entry is bigger than the second in xa and the opposite in xb. So uh, you can show that the hypothesis of the ping pong lemma are satisfied uh, for this set, and consequently the group generated by a and b is actually a free group. Okay, so any questions until now? Okay, great. So now we can move on to the next thing. Can someone confirm if they can hear me? If people can hear me?
Yes.
Oh, okay, great. Okay, so we're gonna now move on to some examples of group actions on metric spaces and what they can tell us. So we want to restrict ourselves to some nice class of spaces, and we also want to impose certain conditions on our action so that we can get meaningful information out of those group actions. So um, okay, so there's a certain class of spaces that I'm going to define now. They're called cat zero spaces, and so why cat? Well, it's just it's an abbreviation for Karta, uh, Alexandrov, and Topokonov, and these were just these are mathematicians, and so they started the study of these metric spaces. So a complete metric space is said to be cat 0 if one, it is a geodesic metric space. So what do I mean by that? Given any 2 points in the metric space, there exists, so let's say x and y are 2 points, and L is equal to distance between x and y. Then there's a map from the interval 0 L. So there's a map from 0 L to the space X, such that gamma 0, such that X and Y are the endpoints of this map. So gamma L is equal to Y, and um, this map is an isometry. So distance between uh, gamma T and gamma T prime is equal to T minus T prime. So geodesics are basically analogs of straight lines between 2 points in in R2. So it's an isometric embedding of the interval uh, of length L into your metric space. Okay, so a metric space is called a geodesic metric space if you have a geodesic connecting any 2 points. Okay, and it's and the second condition that we need is called the triangle comparison property. So what is that? So given a geodesic triangle, which just means there are 3 points, and we consider the geodesic joining the three geodesics joining these 3 points, and let's say they have side lengths, distance AB, distance BC, and distance AC. So what we can do is, taking those three positive real numbers, we can construct a triangle in R2 with the same lengths, and that triangle we call it the comparison triangle. Okay, and we call the corresponding points A prime, B prime, and C prime. And so um, the condition we wanted to satisfy is that uh, you have, so let's say you take this geodesic AB and you look at the time parameter t. So t is some number between 0 and distance AB, and corresponds to some point on this geodesic, and the same is true for t prime, which belongs to 0 distance BC. Okay, and you look at the comparison triangle that that will also give you 2 points, gamma bar t and uh, gamma prime bar t prime. And what you want is, you want the distance between gamma t and gamma prime t prime to be less than um or equal to the distance between the corresponding points in the comparison triangle. So you want your triangle to be thinner than the triangle in R2 in some sense. Okay, so and and then we'll see that a lot of metric spaces do follow this property. So um, okay, so let's look at examples of cat zero metric spaces. So Rn with the with the usual Euclidean metric satisfies this property for, I mean, it's sort of trivial, but if you take any 3 points, you can you can find a plane uh, in which they lie, and that plane is isometric to R2. So you can yeah, here it'll just be an equality in that case. Trees will satisfy the cat zero the triangle comparison property, because in a tree uh, any triangle will be degenerate. So if you have 3 points in a tree, so you have some tree, finite or infinite, and if you look at any 3 points, the triangle will look like, so let's say you had something here, let me change the color. You had x, y, and z. So the triangle between these three looks like so it looks like a tripod. There's a center point, and you have three segments coming off of it, and yeah, and Hilbert spaces. I don't know if you have come across them, but they also satisfy this property, and there are many more examples that I've not listed here. Uh, so yeah, so it's quite a rich collection of spaces that satisfy these properties. So we are going to prove a theorem uh, about isometric groups of cat zero spaces. So we're going to show that if there's a group which acts properly on a proper cat zero metric space, then that group has finitely many conjugacy classes of finite subgroups. So let me just explain what all of these words mean. So properly, um, so that so proper actions. So this means that your group action is proper if uh, given any point, uh, given any point x, um, there's a ball of radius r such that so given x there exists r such that such that if you look at the collection of all group elements gamma such that gamma uh, bxr intersection bxr is non-empty. So all those group elements which map this ball such that it overlaps the ball. So the translate overlaps the original ball. If you look at all such group elements, then is finite, so that collection is finite. Okay. Um, so that's what we mean by proper. And so, and here, when we say that a metric space is proper, we mean something else. Proper metric space. Well, by that we just mean that closed balls are compact. Okay, and here's a small exercise for you guys. Exercise. Uh, for those of you who are familiar with the Hilbert spaces, uh, Hilbert spaces of infinite dimension are not proper. Okay. Great. Uh, right. So now we know what these two words mean. So the conclusion is that it has finitely many conjugacy classes of finite subgroups. So there might be, so given a finite subgroup of gamma, any conjugate is also a finite subgroup, right? But what we are saying is that up to conjugacy, uh, there are only finitely many subgroups, finitely many finite subgroups of gamma. Okay, so let's look at a proof of this. Okay, so this lemma will come in very handy to us. So let me know how I'm doing on time. How much time do I have? Hello, am I audible?
Yeah, you can take your time, like whatever you require.
Oh, okay, no problem. So, so okay, so let K be a compact set, and let us define Rk to be the real number given by infimum of small r, such that there exists x belonging to x, such that uh, the compact set is contained in a closed ball of radius. So this, sorry about this. This should have been x. Okay, so we have a compact set, something like this, and let's say so. Um, in a metric space, a compact set is nothing but a closed and bounded set. Okay, so since this set is bounded, given any x, you can take r large enough uh, such that k is contained in the closed ball of radius r. And now the question is like how small you can make this r. Okay, and so the infimum of all such numbers is what we call r sub k. Uh, we will call it the circum radius of this compact set. So let k be a compact set of a cat zero space, and let r is equal to r sub k. So small r is the circum radius of this set, and then there exists a unique point p such that k is contained in the closure of the ball of radius r around p. Okay, so before going into the proof of this lemma, let's see how this lemma helps us to prove the theorem. So let C be a finite subgroup of gamma. Okay, and pick any point P. Uh, so P is a point, and let us look at its orbit. So this is G of P, where we take G coming from the finite subgroup. This is another G prime P, and this is just a finite collection of points that we get. So now this orbit is definitely a compact set, and it has a if we assume the earlier lemma, it has a circumcenter C. Okay, and notice that this collection of points is preserved by the our finite subgroup. So uh, so this set, so K is the same as GK for all G belongs to the finite subgroup, and now it follows that G must fix C. So G dot C is equal to C. That's because G dot C is a circum okay. So G dot C is a point that satisfies this condition that K belongs to the closed ball of radius r around GC, but but note that there is a uniqueness in this lemma. So both C and GC are the same point because they both satisfy this condition. So GC is equal to C. So it follows that C is a uh, fixed point for every group element in this finite subgroup. Okay, it's we call it a global fixed point for this finite subgroup. Okay. Uh, Now, uh, okay, I think I forgot to mention something in the theorem. So let me just fix that. So it acts properly, and so sorry about this. Properly and co-compactly. I'll explain what that means. Okay. So what do I mean by co-compact action? So what I mean by that is that there exists a compact set K such that if you consider all of the translates of K, uh, G of K under the group action, uh, then it covers X. Okay, so let me give you an example of this. So remember our example of Z square acting on R2 by translations. So now if you consider R2 and if you consider the unit square, okay, so this is the origin and this is 1 comma 1. So this unit square, if you consider all of the translates of this unit square by elements of Z square, then you get the entire R square. And this closed unit square, it's obviously a compact set. So that's what I mean when I say that the action is co-compact. Okay, great. uh, okay, so by assumption there exists a compact set such that its translates cover X. Okay, so now we have our point C somewhere, and this point is fixed by our finite subgroup. Okay, and it belongs to some translate of our compact set. So this is K and this is G of K. And now if you apply G inverse to this, then it'll map the set back to K, and there'll be some point here which will be G inverse C. And if you look at if you look at the conjugate of C by G, so if you look at uh, G C G inverse, then uh, C fixes X implies G inverse CG fixes G inverse. Oh, sorry. Okay, C fixes small c, then G inverse CG fixes small c. Okay, so we can. So now we've just shifted our point and shifted our finite subgroup within its conjugacy class. Uh, so now the okay. So now we just need this final piece of observation to finish our proof. Okay. So this is a compact set, and our group is something that fixes a point in this compact set, and we want to show that there cannot be too many of these things. There can only be finitely many of these things. Okay, and so the way that we are going to do that is that, so we take our compact set and take any point in this set, okay, X, and by assumption of so we have assumed our group action to be proper. So it means that there is a small some small enough number R sub x such that the set of group elements gamma, such that gamma dot x R sub x is intersects with finite. Okay, so for each point we get such a real number, so we get a ball. And so we get a collection of balls around each point. So, and all of these this collection of open balls forms an open cover for K. And owing to compactness, we can say that there is a finite subcover of this cover. Okay, so we get a finite collection of points xi 1 up to n, let's say, and such that this condition is satisfied. So, so our point that we were looking at, G inverse C, is somewhere in here. Okay, it belongs to one of these. It belongs to one of these open balls in K. So let's say G inverse C belongs to Bxi Ri. Then then the subgroup that we were looking at, G inverse CG, is a subset of all of those group elements that we were looking at, is a subset of gamma such that gamma dot p xi ri intersection is non-empty. Great. Okay. So, and we know that this set is finite. Finite. So now, if we just take all such sets for x1 up to for all of these x1 up to xn, and just take the union of all of them, then we get a finite set. And we know that our subgroup is a subset of this finite set. So therefore all such possible subgroups have to be finitely many. Okay, so this finishes the proof. Um, this has to be an inclusion. Okay, so yeah, so that finishes the proof of this theorem. I've not told you the proof of this lemma, which is slightly technical, and it uses the. So yeah, if you want me to, I can stop right now. But let me just finish by saying that there are groups that have infinitely many conjugacy classes of finite subgroups, and so this condition gives you an obstruction that such a group cannot act nicely on a cat zero space. So yeah, I think I'll stop here. That's okay.
Now, if anyone has any question, they can ask you.